Hello everybody. So this is Dr. Sergey Sarkisov, and today we will discuss complex numbers. And we will even solve a really interesting complex equation. Okay, so a polynomial equation that will have not only real roots, but also imaginary, or parts that have imaginary, so complex number roots. So watch this. Let's first begin. Let me give you a quick definition of a complex number. What a complex number is, let me denote it with a z. Okay? What that is it's a real number. Part of it is real. So like, let's say a, plus, and then there's an imaginary component to it. Now, it may be just a real number, and the imaginary component will then be what? 0, so 0i, but this is plus a bi, where I is, again, the square root of a -1. Okay, please remember that, right? So actually, we come up with I when we are wondering, well, what squared is equal to a negative number? And we are struck with, oh no, there's no such number. There's no real number that works. And so if it's not real, a mathematician comes and, what he or she does, they make something up. And that something is a square root of -1, written as I, being the imaginary number. So anyway, there's that. And we want to understand this, right? Again, I is the square root of -1. In other words, when you square I, you get back a -1. It's a negative number. We don't usually consider numbers squared giving a negative, right? Graphically, it's very hard to see those imaginary numbers. Okay? So anyway, let's look at that, right? And let's imagine I'm asking you to solve the equation. Okay? Z cubed plus 1 is equal to 0. So let's solve this. Okay? That's our goal. And I am guaranteeing you by the fundamental theorem of algebra, following that, you will have, because this is a polynomial of degree 3, you will have three solutions, okay? Not just one. So again, if I begin solving it this way, where I'm saying, okay, well, z cubed is equal to -1. Okay, great. What numbers work? -1 works, right? -1, -1, -1. When you cube it, you get a -1. But that's not it. There's only one answer, and something else will not work. Watch this. In fact, if you wanted to slow down and do kind of what we already know, we're able to solve this without any de Moivre's theorem or even the knowledge of the depth of complex numbers. So what you can do is, there's something like the rational zeros theorem, there's a factor theorem. In fact, if you see the -1, that's not z cubed, but if you see -1 works, right? That's one of the solutions, one of the zeros, right? For this, actually, if you put a -1, you get a -1 plus 1 is 0, right? So what would happen is z minus a -1, which means z plus a 1, okay? This is makes the plus 1 because it's a -1, so minus minus. And then times whatever this whatever's left, right? Has to equal to z cubed plus 1. This has to be a factor, okay? And if we do synthetic division of polynomials, as we had done or learned a little bit earlier, we can see that, look, if we use -1, okay, as our 0 or our root, that one, and my polynomial is z cubed plus 0z squared, don't forget the zeros, plus 0z, and then plus a 1, right? And if I'm dividing this polynomial, this is again z cubed plus 1 by a z plus 1, okay, right there, what is going to be that quotient, right? What will it be? What will be the result? Well, synthetic division, and this is called synthetic division. Synthetic. There's also long division, right? Synthetic division. We can do this. We can say, okay, well, bring the 1 down, okay, multiply by -1 this way. So we bring this down, multiply by -1. And you get a -1. Add these up, bring this down. What's a -1 plus 0? It's exactly a -1. Okay. Now multiply this by -1. You get a 1, right? -1 times the -1 is a 1. Add these up, bring them down, you get a 1, right? 0 plus 1. Multiply by -1. You get a -1, right? And add these up, you get a 0. We expected, after I told you there's a 0, that the remainder will be 0. Yes, this means that z plus 1, so z cubed plus 1 is actually, z plus 1 has to be a factor of it, right, because the remainder is 0, and actually the remaining, the quotient, is going to be z squared for that right there. Minus a z is minus a 1, right, coefficients, and then plus a 1, that constant term. And so this is the other part of it, and I'm asking you this, z cubed plus 1 equals 0. So it's now asking you the same as this, the factored form of it. And not always will be this easy. Maybe you will not even have a real or rational or even a real root sometimes. But if you have a real 0, negative 1, right, that makes this nicely factorizable, right? What we can do is we say, well, this is equal to 0. That was trying to solve that this is equal to 0, so this is equal to 0. And then go from here. We have, well, z plus 1 by this 0 product property. Okay? Z plus 1 is equal to 0, right? This is equal to 0. Or how do you make something times something 0? One of those somethings has to be 0. So this is 0, and then we have this z equals negative 1 as a possibility. Or this whole thing is 0. Z squared minus a z plus a 1 is 0. And we can do what? I can't really easily factor that right now, but I can use the quadratic formula. Okay? So what is my a? That's coefficient 1. My b is a negative 1, and my c is a 1, just like we had here, 1, negative 1, 1, right? And so my quadratic formula, okay, quadratic formula, I'll write that, is actually, and we should know this now, it is that x, or now z, is going to equal to negative b plus or minus the square root of the discriminant, which is actually b squared minus 4ac, right? All over 2a. This is just a formula we basically, using completing the square, from the standard form of the quadratic equation, we derived this formula, okay? The quadratic formula earlier on. And so now using that formula, something you can memorize, this result you can memorize now. You don't have to derive it all the time. You can do this. You plug these numbers in, and you have that z here is equal to what? Negative of a negative 1 is a 1, plus or minus. That will give us the two distinct solutions here. They're going to be non-real, okay? They're going to be complex numbers, but watch. The square root of what? What's b squared itself? Well, negative 1 squared is 1 minus a 4, 1, 1, so negative 3, okay? 1 minus 4 is a negative 3, all over 2a, so 2 times 1, and that's equal to exactly what? 1, right? Plus or minus the square root of 3. Now bring the negative 1 out to an I, square root of negative 1 is I, all over 2. And so our set of solutions will actually be what? They'll actually be, so this brings us to this right here with this, to all the solutions being negative 1, and then let's do the plus and the minus. So 1 plus is square root of 3i over 2. And then, of course, the 1 minus is square root of 3i over 2. These are the 3 zeros, the 3 things, 3 numbers, the complex numbers, that make this work. In fact, how do we know that? By checking, let's say. Yeah, negative 1 for sure works, right? Let's say we're going to check. So if I check this, let me just do this. So check, I'm going to say, what does it mean check? So try z equals negative 1. And you do get negative 1 z cubed, right? Plus a 1. And yes, that's equal to 0. So check mark. Now, check z equals, let's just do one of these. Let's do 1 plus root 3i over 2. So again, if I'm to cube that, it may be a little messy, but we can do that. Okay? So let's do this. Then this cubed is 1 half plus, let's separate a little bit like this in 2 fractions. Root 3 over 2i. And I'm going to cube it and then add a 1, and I'm hoping it's equal to 0. This is the left side, the 0 is on the right side. But anyway, let's see what this is equal to. And by the binomial coefficients, if you remember that binomial theorem, this could be a 1, 3, 3, 1 for the binomial coefficient cubed. So you have you have this first term cubed. This a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. So I was kind of fast. Let me show you what I mean by that. You cube this number, first one. Then plus 3, you square the 1/2 now, and you multiply by just 1 time this, right? Root 3 over 2, 1 times that. So without squaring, just first power. And then add a 3 of the 1/2. Now don't square that, but square this root 3 over 2i. Okay. And finally, what do we have? We have the plus this one cubed, right? So plus root 3 over 2I cubed, and then plus a 1 at the very end, right? So this here is that right there. And then let's simplify this further. That's an 1/8, right? Everyone? And then what is this? 3/4, and that's a root 3, so it's going to be a 3 root 3 over 8. It's 4 here at the bottom and 2 here, I. This one will be, and if you square the I, it's going to be a negative, so it's actually a minus. 3 over 8. So 3, what is it? 3/8. And 3, so 9/8, right? Minus 9/8. So there's a 3, and a 3 comes out square root of 3. So minus a 9 over 8, the I goes away. I squared becomes a negative 1. So minus and there's 1 there. And what is this one? This is a 3 over 3 root 3, right? Over 8, because I'm cubing it. I cubed is a negative I. So I'll actually put a minus here, and I here, okay? And all that, and then plus a 1 at the very end. And what is this all equal to? 1/8, right? Minus 9/8, okay? And then this goes away, right? The minus and plus or minus the same thing. 3 root 3 over 8I. And then plus a 1, okay? 1/8 minus 9/8, that's negative 8/8, that's a negative 1. So this is equal to negative 1 plus a 1, and that is equal to 0. Check mark. We wanted that something cubed plus 1 is equal to 0. Now that would be difficult to just guess that number right there. Those solutions there, that would be so difficult to guess. But we did this in a rather algebraic way. I didn't really have to teach you too much about complex numbers besides just knowing what I is, okay? And so that's it. We checked that. We didn't check that last one, but it would be very similar procedure as I did this one. So this is, we did this one and we did this one checking. We didn't do the checking that one. You can, I encourage you to try that on your own. Cube that, add a 1 to it, and see, is it really going to be 0? Okay? Now, let me go ahead and continue a little bit further with something really interesting. We'll use the Euler's formula for a complex number. Okay, so the other way to write a complex number, and this is a very interesting result, it would be like this. You can also say, and any complex number has a modulus and a direction, let's say. If you talk about polar coordinates, or if you're talking about kind of the x and y, and then when you graph it, what's the angle? In fact, look, if you consider a complex number, there's a real, this is a complex number plane, and this is the imaginary part of the complex number. And in other words, that's the A, right, and that's the B. So if I have A plus BI, and let's say A is a positive for some reason, some 3 or 2 or 4, and you go up 2 maybe, so 4 plus 2I or something, that's going to be the number right there. Then if that's 4 and that's 2, that's going to be the number representing the number, that point representing the number 4 plus 2I. So the real part is the right left, it's like the x value, and the 2I would be the y value. And so any point here, that would be the A comma B. That would be this Z. So you can also represent these, all of these points, including these, in the what? Into the complex coordinate plane, the complex plane, right? Complex number plane. So we can graph these numbers. Now look, this is an angle, let's say. Remember that angle? In trigonometry, we learned there's an angle with respect to the x-axis going counterclockwise. Call this angle theta. And this length, call this r, right? It would be the distance from the origin to this point. But actually, r squared by Pythagorean theorem will be a squared plus b squared. And if you think about it, theta, if you do tangent of it, it would be the y over the x. And that would be the y, the b value over the x, the a value. So that would be that a value, right? So what we can do is, when we have that angle and that modulus, or the r, the length, the distance of this kind of the point from the origin, you can also write, and you may not even know the theta and r. You don't necessarily have to find this, but you can also write the z as in the Euler form, okay? And it's written as Euler, but really that's said as Euler, strangely enough, right? But that's how his name is spoken. In fact, just as an interesting thing, so I have my PhD, right, from a French advisor, a very renowned, actually, mathematician himself. And if you look at that math genealogy kind of tree, there's something like that on, like Google it, whatever. You will find, that's kind of cool. I didn't know that myself, but I trace back down to, doesn't make me any better than, but I trace back down from, like, Euler was one of the ascendants of mine. It's kind of cool, right? Like, you have Euler, I think there's Lagrange and Poisson, or Lagrange was Euler's, but there was Poisson, there was Lagrange, and then Laplace, they're all there, and it's kind of like, wow, I have like a French, because my advisor was a French mathematician, Robert Azencott, okay? So anyway, let's do this. It's a really cool guy. It's one of my favorite mathematicians. So anyway, z, you can write it as r, and then e to the I theta. And in trigonometric ways, this actually means z is equal to r times cosine of the theta. And that, remember, has to do with the x value. Cosine is the x component, and giving you the x component, and then plus I sine theta. Okay, where that's going to give you the r sine theta is going to be the y value, the b. So you're going to have, this is a plus I b, or bi. Okay, this is r sine theta is b, the y value. Okay, so knowing this is pretty cool, because what we can do later is, if I told you what's z cubed, let's do this. Let's color here. What is z cubed? You'll look at it and you're like, well, I don't want to cube all this, right? But what you can do is you can use this first expression, the Euler's formula here, and you can say, well, that's just r cubed, e to the I theta, so a cubed e to the I 3 theta. Okay? Kind of cool, right? And then you can do that. I'm just cubing this, right? So I'm cubing this, I get from there to there, and then I'm like, hey, if I do this if I get from here to another form, right, the trigonometric kind of looking form, you actually can do this. You can say, well, that's r cubed. I'm using now, this is the modulus r cubed, so r was r, now r cubed is r cubed. And then look, cosine of, now not theta, but 3 theta, okay, so I'm using the angle 3 theta, plus I, right, sine of the angle now 3 theta. I'm using that angle 3 theta then, okay? And that is really nifty. Actually, this is basically, we're using de Moivre's theorem. It's a French mathematician. Okay. And de Moivre's theorem just extends this a little further, this result, to any n. So if I told you z to the 5th power, you would have r to the 5th cosine 5 theta plus I sine 5 theta. You would have a 5 theta instead of a 3 theta. In fact, if you have basically a number, let's say a complex number, r times, so r cosine theta, right, the x value, plus I sine theta, which we can just say that's represented by the modulus equivalent to r comma theta. Let's depict it that way. So there's an angle, there's a modulus. That's what we're talking about, the kind of the r and the theta, and you can see where that point is. So that you can get from there the a and the b. Okay, so this is actually r outside of all this, right? And so let's do that, and then look, I'm going to depict it this way. I'm going to take it to the nth power, any power, okay, nth power, especially any natural number. And we're going to get what? We're going to get r to the n, and then we're going to use that angle cosine n theta, like I was doing 3 theta here. Okay. Plus an I sine of n theta. Okay. It's really, really beautiful result. You'll see how we can use that in a moment. And then what happens is that's the same thing as not r theta to the n, but you can write it also as r to the n, because we have now the modulus is r to the n power. Theta and n is you actually multiply, so n times theta, like we had 3 theta. Remember for the cubing, 3 theta, you triple the angle, now you're going to n times the angle. Okay? So this number, when you take it to the power n, will go to this number. The modulus is taken to that power, and the angle actually multiplies by that power. It's kind of cool, right? So what should we can do with that? Let me erase some of this, and let's see if we get back the same solutions. So watch this. We will get, to still solve, z cubed plus 1 is equal to 0. But this is a lot quicker, right? I would say. It takes some trigonometric understanding, of course. But what we can do is this. Z cubed plus 1 is equal to 0. Let's say we kind of understand some of these results going in. Okay, and you'll see how I'll use that. To solve this, I would do this. Okay, z is some number. Let me represent it by, so I'm going to say r cosine theta plus I sine theta, which is exactly, again, the representation I want to give this is r comma theta. Like I know the modulus, okay, and I know the angle that it's at, the direction. Kind of like vectors, right, where you have the magnitude of the vector and the direction. So it has the scalar component and the what? And the direction, where you're going component. I always, when I talk about vectors, I always say, look, or even these complex numbers really represent vectors in a sense, right? Because you kind of have the where it is located, okay, where you're going, and how long you're going. So I'll talk about directions, like let's say you travel from point A to point B. When you talk about numbers like lengths, well, I know from A to B there could be a distance of, let's say, 2 miles, okay? But where is it from here to there? Do I go this way? Or do I go that way at an angle, right? And so that, like the motion, how long with the direction will tell me exactly where I'm going to get from where I'm starting. And that's really interesting, I think. So anyway, going back to this, what I can do is, if I do z cubed, what's z cubed? Z cubed, we're going to do this. It's equivalent to r cubed comma 3 theta, right? And so in other words, I'm going to do this. I'm going to say, okay, I'll put the negative 1 over there as well, right? I'm going to subtract the negative 1, the 1 from here, so you get a negative 1 on the right side. Then I'm going to say, okay, so z cubed, right? And this is what? This is r cubed times cosine 3 theta plus I sine 3 theta, okay? And that's equal to negative 1. Now, what's the modulus of the negative 1 itself? And the cube root of that? I'm going to get, for that basic number, how long is it? Like, how long is this negative 1? And the cube root of that? It's a 1. So it may take some experience for you to get that, but r is, I'm not going to say negative 1. I want to say a positive number. I'm just going to say 1. Okay? And so let's take care of the 1. Now, we're left with cosine 3 theta plus I sine 3 theta, because the 1 goes away, right? Sine 3 theta. And if this was an 8 or negative 8, you would have done a 2. If this was, let's say, a 2, you would have done cube root of 2, okay, for r. But we're just going to do, for negative 1, we're just going to do a 1. You could do negative 1, but then it would be a little different with the angles. So again, you just put the 1 to positive. If it's a negative, we make it an absolute value, so positive. And you have this is equal to what? We're left with a negative 1, right? Now, this is imaginary. This is real. There's an I here. There's no I here, right? In fact, I can put plus 0I, or plus I times 0, right? So I have to match up the real and the imaginary. The real is cosine 3 theta is equal to negative 1, right? And the imaginary part match up with sine 3 theta is equal to 0, right? I sine 3 theta, I 0. Okay, so how do we do this? Well, when is cosine of what angle is negative 1? And we know that's a 180 degrees, okay? Or a what? A pi radians. So this is actually 3 theta. That angle actually is 3 theta, and it's equal to pi radians, okay? And of course, I'm going to raise the word radians in a moment. You can also add a bunch of circles. That's a big trick as well, right? So you can always add like 360 degrees every time to get back to where you started, or subtract the circle to be allocated in the same position. Like what I mean by that is, if let's say this angle is, let's say, 225 degrees, you can do another 360 addition. 360 addition, you'll get back to the same spot, the terminal side. Or subtract 360, you get negative 135. That's the same spot, same angle for what matters there. So we have 3 theta is pi plus a 2 pi k plus a bunch of circles. K could be an integer. It would be 0 when you just are talking about that, right? And then this one, of course, gives you, that takes care of this. Okay, so now, to solve this, let's divide by 3. Theta is equal to pi over 3 plus 2/3 pi k. Okay? And then look, what this is we can say, okay, well, pi over 3, okay, great. Let's add another 2/3 pi. What's pi? 1/3 plus 2/3 pi? It's pi. 3/3, right? And then add another 2/3 pi, you get 5 pi over 3. So these are the thetas. And you may wonder, what about the other ones? What about the other ones? Well, if I go on and on, whether I go left or right, like if I go negative or positive, like let's say I do a 7 pi over 3, continue there, and then a 9 pi over 3, that's a 3 pi, right? This 3 pi is exactly already the pi, right? We already used it. Here, we don't have to do it again. 7 pi over 3, that's going to turn out to be this one, kind of the same location. So we only will have 3 locations left. I didn't want to cross that out, which is pi over 3 pi and 5 pi over 3. And this is really confusing for some of us who really have not done any of this complex number stuff before. But for our class, where we have looked at this quite a bit, right, extensively, I think this is something, a familiar result and a good review of it. So now let's use the theta as one of these, and the r is a 1 to get their solutions. In other words, here's what I mean by that. Our final answers. We're almost there. We almost have the final answer. Watch. So we would have. Let's first do the pi. Pi is an easier angle to work with, I think. So let's try theta 1. And r is always the 1 we're using. Theta 1 would be, let's do the pi over 3 for theta 1. But look at this. Theta 2 was a pi, and theta 3 was a what? 5 pi over 3. So let's look at my z. My z1 will be r comma theta 1. And again, because r is the same everywhere, right, it's a 1. Z2 is going to be r theta 2, represented by that. And Z3 is going to be r theta 3. So I'm telling you, these are the 3 solutions for this equation. But that doesn't help us that much. Like, what are they actually, right? So let's look at that as, remember, what does this mean? It means r sine of the angle plus r cosine of the angle, right? Well, that's the real part, the x value stuff. And then plus r sine of the angle and I, right? Okay. I want to do z2 first. It's an easier number to work with. Look at this. So this is r cosine theta 2 plus r sine theta 2I. And we're going to do this first after I write this z3, which is r cosine theta 3. I'm using the third theta plus r sine theta 3I. Now we have the theta 1, 2, and 3. We're going to use it all and plug it in. And we finally get this. So what's 1? That's not going to work. What's 1 times, let's do this one first. So what's 1 times cosine of pi? So it's going to just be cosine of pi, right? Plus sine of pi, I. And you know what cosine of pi is? We talked about that. That's a -1. It's the x value minimum that you get from a cosine. And the sine of pi, that's just a vertical, is the 0, right? On a unit circle in the zero, right? So you get -1 plus 0I. That's just a -1. We had that before. If you remember, our solutions were -1, and then other material was what, 1/2 plus the √3 over 2I, 1/2 minus the 3 over 2I. That's what we got before by doing something different. And the algebraic result. And we can still do that algebraic because this is a very approachable problem that way. But if this was a z to the 5th power, then you would have to do it basically the way we're doing it now. So again, we checked this out. This worked. Let's try z1. So it's what? 1 cosine theta 1. So just forget the r, because r is 1. What's cosine of theta 1? Cosine of pi over 3. That's 60 degrees. Pi over 3 radians is 60 degrees, and that's a 1/2. It'll turn out to be. And plus a sine pi over 3I. So you'll see this is going to be 1/2 cosine pi over 3, and this is sine pi over 3. You should remember that sine of 60 degrees is at √3 over 2. So plus √3 over 2I. Oh, you know what? That worked. Okay, this is also working. That's right there. We weren't making any guesses. We actually got that before that result that we got. It was the correct result more than likely. Let's check that final number. So r cosine theta 3, so it's cosine of what? 5 pi over 3? That's the what? 300 degrees. No? All right. And so that's going to be, this cosine is up in quadrant 3. So look, you go 180, right? Let me see, you go 180, and then 270 and 30 more, 300. It's in quadrant 4. Cosine is positive, sine is negative. So it's going to be this, plus sine of 5 pi over 3. A lot of nuances I'm skipping here, of course. So hopefully you just kind of fill in those blanks that I'm missing, right? And so you have this. Again, this is still a 1/2. You can check that in the unit circle. It's what? There it is. The reference angle is 60 degrees there. That's my 5 pi over 3. I'm doing kind of mixture of radians and degrees to help you see that. And so cosine is going to be a 1/2, and the sine is going to be a negative root 3 over 2. Okay? So you have 1/2, and then minus a root 3 over 2 I. So you have to be very familiar with the trigonometric functions of the common angles. This, yes, it's there. This, yes, it's there. And this, yes, it's there. There's that last one we did. All right. So hopefully that was helpful and interesting. And I'm going to stop here. But continue on and maybe try like z to the 5th plus 1 is equal to 0. Okay? And one more thing is you could graph these points. You can graph these complex numbers. And just a quick side note. So look, if I do a -1, 0, this number -1 plus 0 right there, or -1, it's right there on the real axis. The real, right? It's a real number. If I do 1/2 and then that's half, right? So that's a 1. Let's say this is a -1, 1, -1. If I go half and then root 3 up root 3 over 2 or down root 3 over 2, I get these points. If I have the unit circle, all of these points make actually an equilateral triangle. Yeah, on the unit circle. These are points of unity. It's really cool, right? So consider that, and if you do z to the 5th plus 1 is equal to 0, you'll have 1, 2, 3, 4, 5 points. They'll make a pentagon. It's really beautiful, this De Morgan's theorem, complex numbers, all that. So, okay, thank you so much.